Let ABCD be a parallelogram with diagonal intersection M such that the circumcircle of ABM, here in green, intersects with line AD, here, in the point E. And the circumcircle of EMD, here in green, intersects line BE, here, in the point F. All right. Then we need to show that these two angles, ACB and DCF, are the same. So, first thing to notice is that we are talking about a parallelogram. So, the angles here, BAM and DCM, are going to be the same. I'm going to call them alpha. And equally, we have that MAD, I'm going to call it beta, is the same as MCB. All right. Now, let's use the inscribed angle theorem on the circumcircle of ABM to state the following. The angle MAE, so this angle, beta, will be the same as the angle MBE here. See it? With the inscribed angle theorem. So this angle is also beta. So now comes the fun part of the problem, where we're just going to construct their tangent to the circumcircle ABM to the point B. So right here in white, I'm going to draw it. So it passes through the point B and is tangent to the circle ABM. And the idea of this tangent, if you might ask, why the hell did I put a tangent in here? Is there a reason for that? And the simple thing is that we can now use the alternate segment theorem that I'm first gonna draw it in general. And it says that you have a circle and a triangle inside, like this. Then if you have a tangent that passes through a corner of the triangle, so it's a tangent to the circle, then this angle here will be the same as this angle here. And so in our problem, that translates to the fact that the angle that I'm going to draw in here is exactly equal to alpha. See? So this angle equals this angle by the same drawing I showed here. So let us just draw in an alpha here. And furthermore, we can use, again, the inscribed angle theorem on the big circle again, so ABM. I'm just going to call the big circle ABM. I'm just going to call it big circle, and the other one, MED, I'm just going to call it small circle up from now. And so we can use it on the chord BM to say that BAM is the same as BEM. And so I'm going to draw an alpha also here. But then immediately, because we have that FM is a chord of the small circle, we can again use the inscribed angle theorem, this time on the small circle, to show that this angle, FEM, which is just alpha, is the same as FDM here. So this will also be alpha. I'm going to draw this in white, the connection FD, because it's going to be important in a second. All right. So until now, we have just done a bit of angle chasing, making angles equal. And now we're going to extend this line FD, oops, just going to extend it a bit further such that it cuts AB. I'm just going to call this point P, whatever, doesn't really matter. But what we notice now is that here we have alpha, and here we have also alpha. And these two lines with these two make up a square. For now we just know it's a square. But if these two angles are alternate interior angles, this must mean that PD and this line, so I'm going to call this point here Q, PD and BQ are in fact parallel. And now we can use that as well to say that PF is just parallel to this part, just because we're just taking a path from the entire PD. PF is inside of PD. So PF is also parallel to this side. And so this angle here is also an alternate angle of this one. So these angles are the same. So we're going to call this also alpha plus beta. Here, this is alpha plus beta. And so then, if we have alpha plus beta here, this means that we also have alpha plus beta on this side here. It's hard to draw this in now, but I'm going to try here. So this means now that I don't know which color to use. This angle here, I'm just going to call it gamma, plus alpha plus beta, make up an entire 180 degrees. Alright? So I'm going to write this down on the side. Alpha plus beta plus gamma equals 180 degrees. And this is now the key to our solution. We are going now to look at the quadrilateral B, F, C, and D. So in correct order, B, C, D, F. What is so special about this quadrilateral? Well, this angle and the opposing angle, which is exactly alpha plus beta, equal 180 degrees. So this angle is concyclic. I mean, this quadrilateral is concyclic. If two opposing angles equal 180 degrees, then this means that these two angles here will also need to equal 180 degrees in total, as the total sum of the angles in the quadrilateral is 360. And this means that these 4 points, so B, C, D, and F, they must lie on a common circle. I'm going to try to draw it. It's not going to be very successful, but oh well. So now, this basically shows us our result, because for a final step, we can now finally use again the incorrect angle theorem on this new circle that we draw on over the chord FD, to see that FBD, which is nothing else than beta, must equal FDC, which is exactly the second angle that we have marked with the interrogation symbol, which is also going to be beta. So we have shown that both angles, this one and this one, are beta. We know that this one is beta because at the beginning we just denoted it by beta, saying it is just equal to this beta, just because it's a parallelogram. We defined it as beta in the start, and now we have finally come to prove that this second angle is also beta. I hope you've enjoyed this beautiful proof of geometry, and I hope this just shows how random constructions and a lot of inscribed angle theorems can lead to such a beautiful solution.